Chapter 20, Electromagnetism. Let's look at the magnetic effects of a current carrying conductor. First, the magnetic field patterns. So if there's a straight current carrying wire, the magnetic field will consist of concentric circles, and the magnetic field is stronger nearer to the wire. We can predict the direction of the magnetic field using the right-hand grip rule as introduced in the previous chapter. So imagine if you have a current that is coming out of the paper. It can be denoted as a dot. We can draw the magnetic field lines around the conductor. And how do we figure out the direction? The thumb for the right-hand grip rule will be pointing in the direction of the current. Your fingers will be the direction of the magnetic field. So your finger is wrapping around the conductor, which means the magnetic field for an upwards pointing current, it will be anti-clockwise direction. So you can add in the direction of the magnetic field. If we were to increase the strength of the magnitude of the current, similarly for a current that's coming out of plane of the paper, you realize that the magnetic field lines will be closer and more concentrated near the wire. So similarly, you use the right-hand grip rule. You can actually find the direction of the magnetic field, which is also anti-clockwise. Remember that the spacing between the magnetic field lines actually represents the magnetic field strength. So for a current I1 that is smaller than I2, the magnetic field lines are more concentrated for I2. So now, if we were to change the direction of the current to into the plane, or which means away from you, you can denote it as a X. Now, using the right-hand grip rule, you can find the direction of the current as well. So with the right-hand grip rule, it will be clockwise direction. Clockwise. Okay, let's look at the magnetic field patterns of a solenoid. So a solenoid is like an electromagnet. It behaves like a bar magnet when there's current running through it. So using the right-hand grip rule, but this time the thumb is pointing in the direction of the magnetic field, which means where the thumb is pointing is the north pole, where the bottom of the palm is the south pole. And as the fingers wrap around the solenoid, this is actually the right-hand grip rule. You can see that the magnetic field lines are mostly concentrated at the poles, because this is where the field is the strongest. To increase the magnetic field of a solenoid, we can actually increase the current, or we can increase the number of turns per unit length of the solenoid, or add a soft iron core. The soft iron core is actually the one that helps to concentrate the magnetic field within the solenoid and actually increases the magnetic field strength. In the previous chapter, chapter 19, Practical Electricity, we did mention about the circuit breaker. So circuit breaker is a safety device that switches off the electricity when there's a excessive current flow, or if a current of a greater than the rating goes through the circuit, you want to stop it. Okay, so figure A is actually the circuit breaker when the current is lower than the limit. So when the current is lower than the limit, the solenoid, which is here, is a weak electromagnet. It's unable to attract the iron bolt. Okay, so the circuit, this is a switch, is closed. So it's a closed circuit. But when a current that is larger than the limit, okay, your solenoid becomes strong enough, okay, to attract the iron bolt, which releases the spring. So now the circuit is open. Okay, so this actually prevents the current from flowing through. And you can easily reset the circuit breaker by hitting the reset button here. So this is a more convenient way as compared to a fuse, where a fuse will break or burn and you have to replace the fuse. Now let's look at the motor effect, which is the force due to magnetic fields. Let me introduce you to the Fleming left-hand rule. Okay, Fleming left-hand rule is used to deduce the direction of the force, okay, acting on a current carrying conductor in a magnetic field. So force F, which will be your thumb, magnetic field M will be pointing in direction north to south direction, and then finally the current, which is conventional current I, conventional current. So father, mother, child. C for current. We can apply Fleming left-hand rule to this current setup where there is a strong magnet, okay, and a power source which runs a current through this magnetic loop. Okay, so we want to determine the force on this magnetic loop. First, you have current running through here. So current is I, which is also C, and that is your middle finger. Then the magnetic field is from north to south. Magnetic field, north to south, which means your thumb will be pointing upwards. And that is where your force will be. So current, force, father, mother, child. Force, magnetic field, and current. And as a result, the loop actually swings upwards. So this motion is also known as the motor effect or catapult effect. Because when a current carrying conductor is placed in a uniform magnetic field, the field will interact with the magnetic field of the current carrying conductor, and this will actually exert a force on the current carrying conductor. So you can see when you have a current carrying conductor, there will be its own magnetic field. As it interacts with the strong magnetic field of a bar magnet or even a solenoid, there will be a force, because you see there's concentrated magnetic field here as compared to here. So there will be a force outwards to push it out. Okay, now let's look at the forces on the pair of parallel carrying wires. Using the right-hand grid rule, we can actually determine the direction of the magnetic field. So if it's coming towards you, the magnetic field should be anti-clockwise direction. It should be in the anti-clockwise direction. But if it's going in plane, okay, it should be a clockwise direction. So you realize that both of these magnetic fields are not synced. So as a result, they repel each other. There'll be a force away. However, if both wires are carrying current in the same direction, in this case, since the magnetic field is both in the same direction, and this will be anticlockwise, they will complement each other, and as a result, this magnetic field will link up, and there will be a attractive force towards each other. So current in the opposite direction repel, while conductors carrying current in the same direction attract. Okay, next, let's look at the force on a beam of charged particles. Okay, so using Fleming's left-hand rule as well, okay, we can actually determine the force acting on each type of particle, whether is it positive charge or a negative charge. So for a positive charge, if it goes towards the right, current is actually in the same direction as your conventional current for positively charged particle. So with a in-plane magnetic field, so let me redraw this. A magnetic field is going into the paper using Fleming's left-hand rule. Current, C, is going to the right, which will result in, using Fleming's left-hand rule, you get a force upwards. So, thumb pointing up, index finger pointing into the paper, current, which is your middle finger, pointing to the right. So, particle bends upwards. For this case, magnetic field into the paper, M, current, opposite direction. Because remember that electron flow is opposite to the conventional current flow. So if I is like this, electron flow is in the opposite direction. So current opposite direction, your force is now downwards. Father, mother, child. So as a result, the particle bends downwards. Okay, for this example, now we reverse the magnetic field. So magnetic field is out of the paper. Current is due to the right because it's a positive charge. So where is the force? It will be downwards. Particle bends downwards. For this example, current is now to the left because electron flow is opposite to conventional current. Magnetic field is out of the paper. Force will be upwards. So the charged particle will move upwards. So to create a larger force on such charged particle, I can either increase the charge, okay, or I can increase the magnetic field. If I were to reverse the charge from positive to negative, the direction will reverse. If I reverse the magnetic field direction, the force also will reverse. Let's look at work example 1, where a current carrying wire is placed between the poles of a magnet, and now we have to determine the force. So for magnetic field, always north to south. So pointing north to south. This direction is the magnetic field. The current, as you can see, the battery was here. It flows this way. So current is this direction, C. So father, mother, child, your thumb will be pointing upwards. And the answer is A. Next, let's look at example 2, where a beam of electrons is entering a magnetic field. They ask you to determine the direction of the deflection. So we mentioned electron beam is opposite to the direction of current. So I will be in this direction. Magnetic field is into the page. So using the Fleming left-hand rule, father, mother, child, you will find that the force is downwards. So your beam of electrons will bend to the bottom of the page. Okay, next, let's look at the turning effects on a current carrying coil in a magnetic field. Okay, so if you have a current carrying conductor, there's a current running through it also in a magnetic field, you can use Fleming left-hand rule. So once again, Fleming left-hand rule, magnetic field, north to south. Your current, child, upwards, force will be in way. Here, force. Okay, using Fleming's left-hand rule. If you were to reverse the direction of current, which is in this direction now, same thing, your magnetic field is still north to south. Your force this time will be outwards. And if you were to pivot this setup at P and Q, you'll cause this coil of wire to turn. And that's where you get the turning effect of current carrying coil in a magnetic field. And if you want to create a larger turning effect, what I need to do is to increase the number of turns or increase the current in the coil. So this functions is actually for a DC motor, which converts electrical energy to mechanical energy. Okay, it's used for drones or your RC car. Okay, and this is a schematic diagram of how an electric motor works with a rectangular coil, carbon brush, your power source, as well as a rheostat. You need to know the function of a split ring commutator, which is to reverse the direction of the current in the coil every half revolution, so that the coil will always be turning in one direction, either clockwise or anti-clockwise. Previously, we mentioned the use of a soft iron core. Okay, a soft iron core concentrates the magnetic field lines and increases the magnetic field strength, as shown here. See, concentrates here. And then with a stronger magnetic field, it will give rise to a stronger force. To increase the turning effect, I can just increase the number of turns in the coil, increase the current, or like we mentioned, add a soft iron core. Okay. So let's look at work example 3. Okay, the diagram shows a simple DC motor. On the right, the gap between the two halves of the split ring commutator is so large or so wide that a carbon brush can only touch one side of the split ring at any time. Okay. Then this protects the circuit. So which means it also sometimes the motor will not start when switched on. So first of all, explain why the carbon brush must not be allowed to touch the both half of the split ring at the same time. Okay, this is to prevent a short circuit as there's no resistor in the circuit. If you observe the circuit carefully, this is the part they're talking about. This is the carbon brush. If this carbon brush is touching the other split ring commutator, this circuit highlighted in yellow will be on its own, and you can see that there's no resistor. I mentioned before, if there's no resistor in the circuit, the wires itself, the resistance becomes significant, and you start heating up the wires. So next question is, why does the motor not start when sometimes it's switched on even though there's no friction? So the carbon brush may not be in contact with any of the commutator, and then it is an open circuit. Okay, and that's all for this chapter.